There's a moment coming, a moment when the last star in the Milky Way will flicker and die. When our galaxy, this magnificent spiral of light, will finally completely run out of fuel. And here's what almost nobody tells you about this moment, what gets lost in the numbers and the timescales and the scientific terminology. It's not sudden. It's not dramatic, like a light switch being flipped. There's no cosmic alarm that goes off, no warning siren echoing through the void. It's slow, so incredibly, incomprehensibly slow that if you could somehow live to witness it, if you could somehow exist for trillions upon trillions of years watching and waiting and marking time, you would barely notice it happening from one millennium to the next. The universe doesn't end with a bang, despite what the poets and scientists and philosophers have told us. It ends with the quietest whisper imaginable, a gradual dimming so gentle you'd miss it if you blinked. A fade to black so prolonged that the word eternity starts to feel inadequate, starts to feel like it's not quite capturing the true scope of what we're talking about here. Let me try to help you understand the time scale we're dealing with. Think about how long a human lifetime feels to you. Really think about it. Remember back to your earliest childhood memories. Maybe you're 5 years old, maybe younger. You can probably recall maybe a few moments, a few images, a feeling or two. Now, think forward to where you are now. Every birthday you've celebrated, every summer vacation, every winter holiday, every first day of school, every friendship formed and lost, every love, every heartbreak, every triumph, every failure, every conversation you've had, every meal you've eaten, every sunset you've watched, every single moment packed into 60 or 70 or 80 years if you're lucky. That's a lifetime. That's the longest thing most of us can really comprehend from personal experience. It feels long when you're living it, doesn't it? Childhood feels like it lasted forever. Your teenage years seem to stretch on endlessly. But then you hit your 20s and suddenly time starts accelerating. Your 30s fly by. By the time you're in your 40s or 50s, years are passing like months used to. Time compresses. And before you know it, you're looking back across decades that feel like they happened in fast forward. Now, I want you to imagine something. Imagine that your entire lifetime, all those years, all those experiences, all those moments, imagine that all of that is just 1 second, just one tick of a clock, one heartbeat. In the blink of an eye, your entire existence from birth to death compressed into a single second. On that time scale, where a human life equals 1 second, the universe as it currently exists, 13.8 billion years old according to our best measurements, has been around for about 436 years, just over 4 centuries. That's all. The Roman Empire lasted longer than that. The Byzantine Empire lasted longer than that. Some families have genealogies that stretch back further than that. So, on this adjusted timescale where your life is 1 second, the entire history of the universe from the Big Bang to right now, all of cosmic history, is less than 500 years. But here's where it gets truly mind-bending. On that same timescale, the time it takes for the Milky Way to truly die, for the last red dwarf star to finally exhaust every last bit of its hydrogen fuel and wink out of existence, is more than 300,000 years. 300 millennia. That's longer than our species has existed. That's longer than we've been building civilizations, longer than we've been painting on cave walls, longer than we've been telling stories around fires and looking up at the stars and wondering what they are and where we came from and where we're going. And we're not even close to done yet. Because after that last star dies, the galaxy doesn't disappear. Its remnants persist. White dwarfs cooling slowly in the darkness, neutron stars spinning silently, black holes lurking invisibly. All of these objects continue to exist for timescales that make the death of the last star look like an eye blink. The white dwarfs take trillions of years to cool completely. The black holes take even longer to evaporate. And by the time it's truly, completely over, by the time even the black holes have faded away through a process called Hawking radiation that we'll talk about later, by the time the very last photon of energy has been radiated into the void and there's nothing left but a thin soup of elementary particles spread across distances so vast they make the observable universe look like a grain of sand. We're talking about timescales where your entire human lifetime, that 1 second on our adjusted clock, would need to be multiplied by more than the number of atoms in the entire observable universe. Let me say that again because it's important. To reach the true end of everything, the point where the universe has reached maximum entropy and nothing can ever happen again, you would need to live not just one lifetime, not just a billion lifetimes, not even a number of lifetimes equal to all the atoms in your body, or all the atoms on Earth, or all the atoms in the solar system. You would need to live a number of lifetimes equal to all the atoms in the observable universe, which is roughly 10 to the power of 80 atoms. And then you'd need to live that many lifetimes again, and again, and again, multiplying it over and over until the numbers lose all meaning, until mathematics itself starts to feel inadequate to capture what we're trying to describe. Our entire human history, from the first humans in Africa to right now, every empire that rose and fell, every pyramid built, every book written, every song sung, every war fought, every baby born, every person who ever lived and loved and laughed and cried and died. All of it, all of human history compressed together is less than 1 million years. But the timescales we're talking about for the death of the Milky Way measure not in millions of years, not in billions, but in trillions and quadrillions and numbers so large we have to start using exponential notation just to write them down. 10 to the 14th years, 10 to the 40th years, 10 to the 100th years. These aren't just big numbers. They're time spans so vast that they break our intuition, that shatter our ability to comprehend duration, that make the word forever seem inadequate. And yet, despite all of this, despite these incomprehensible timescales, despite the fact that we're talking about events so far in the future that they might as well be infinite, there's something profound we can learn from understanding this journey. Something important about right now, about this moment, about your life and your existence in this particular cosmic epoch. Because here's the thing. Here's what makes all of this worth understanding. Right now, in this instant, you are living during what future cosmologists, if any could exist, would call the golden age of the universe. You are alive during the stelliferous era, the age of stars, the time when the cosmos is filled with light and energy and possibility, when galaxies shine brilliantly across the void, when planets can be warm enough for liquid water and complex chemistry and maybe life. You are here during the universe's prime, during its youth and vigor, during the time when things are actually happening, when structure and complexity are possible, when consciousness can emerge and contemplate its own existence. And most of us, most people walking around on this planet right now have absolutely no idea how special that is, how rare, how temporary, how precious. So why am I telling you all of this? Why spend your time, which is valuable and finite and never coming back, learning about the death of the galaxy billions and trillions of years in the future? What possible relevance could this have to your life right now, today, in this moment? Let me explain, because this is crucial. This isn't just an astronomy lesson. This isn't just about cool space facts or big numbers or scientific curiosity, though all of those things are part of it. This is about perspective. This is about understanding time and existence and meaning in a way that most people never do. This is about looking at your own life, your own concerns, your own anxieties and dreams and fears, and seeing them in their proper cosmic context. Not to diminish them, not to make you feel small or insignificant, but to help you see what actually matters and what's just noise. When you truly understand, when you really let it sink in, that the universe will continue for time scales that dwarf human comprehension, when you grasp that we're living during a brief window of cosmic possibility, when you realize that you are here now, during the time when stars shine and life is possible, something shifts inside you. The things you worry about, the daily stresses that fill your mind, the anxieties that keep you up at night, they don't disappear. They're still real, they're still important to you, but they get reframed, they get placed in context. You start to see that you're participating in something extraordinary. You're alive during the era when the universe is most interesting, most dynamic, most full of potential. You're made of atoms that were forged in the hearts of stars billions of years ago. You're a way for the cosmos to know itself, to understand itself, to appreciate its own vastness and beauty and complexity. You're a temporary pattern of matter and energy that has somehow become aware, become conscious, become capable of looking up at the night sky and understanding what you're seeing. And that's not nothing. That's not insignificant. That's remarkable beyond words. This video is for anyone who has ever felt overwhelmed by modern life. For anyone drowning in responsibilities and deadlines and expectations. For anyone who lies awake at night worried about things that might happen or things that already happened. For anyone who feels like they're just going through the motions, like life is passing them by, like they're missing something important but they can't quite figure out what. Understanding the death of the Milky Way, understanding the full timeline of cosmic history from beginning to end, gives you something that's hard to find in our fast-paced, always connected, constantly stimulated modern world. It gives you perspective, deep, profound, life-changing perspective. It helps you see that your time here is limited, not in a depressing way, but in a way that makes every moment more valuable. It helps you appreciate that you're living during an extraordinarily special time in cosmic history. It helps you understand that the light you see when you look up at the stars at night, that light is temporary, and that makes it more beautiful, not less. The stars are burning through a finite fuel supply. When it runs out, they die, and they're not coming back. There's no second chance, no reset button, no do-over. Once the last star has burned out, once the last photon of starlight has faded into the cosmic darkness, the universe will never shine brightly again. This is it. This moment. This era. This is the time of light and possibility. And you're here for it. You won the cosmic lottery just by being born during this epoch instead of during the dark ages that came before the first stars formed, or the even darker ages that will come after the last stars die. You exist now, during the good times, during the brief window when consciousness and complexity are possible, and that makes your life, your experiences, your relationships, your moments of joy and connection infinitely precious. Not because they last forever, but precisely because they don't. The fact that stars burn out makes their light more valuable. The fact that life is temporary makes it more meaningful. The fact that you only get one chance to experience this particular moment makes it sacred in a way that something eternal and unchanging could never be. So, this video is going to take you on a journey through time itself, not human time, not historical time, but cosmic time, deep time. We were going to start here now, in the stelliferous era, with our beautiful spiral galaxy full of bright blue young stars and ancient red giants and everything in between. We're going to watch as the Milky Way collides with our neighbor galaxy Andromeda, a cosmic event that will completely reshape our galactic home. We're going to follow the slow, gradual decline of star formation as the galaxy runs out of hydrogen fuel. We're going to witness the death of the last stars and the beginning of the degenerate era, when only stellar corpses remain. We're going to see the black hole era, when even those corpses have decayed and only black holes persist. And finally, we're going to reach the dark era, the heat death, the maximum entropy state where nothing can ever happen again because all the energy in the universe has been evenly distributed and there are no more gradients to drive change. It's going to be a long journey, but I'm going to be with you every step of the way. I'm going to explain everything in clear, simple terms that anyone can understand. No confusing jargon, no assuming you already know advanced physics. Just straightforward explanations of what happens, why it happens, and what it means. And along the way, we're going to find moments of profound beauty, moments that take your breath away, moments that change how you see the universe and your place in it. Because even though this is ultimately a story about death and ending and the fading of light, it's also a story about the preciousness of existence, about the miracle of consciousness, about the extraordinary gift of being alive during the time when the universe shines brightest. So, if this kind of deep exploration speaks to you, if you're interested in understanding your place in the cosmos, if you want to gain perspective that will change how you see your own life, then please consider subscribing. Hit that like button. It genuinely helps more people find these videos, helps more people gain this cosmic perspective, helps build a community of people who care about understanding the bigger picture. And now, let's begin our journey. Let's start where we are, in the stelliferous era, with our Milky Way galaxy alive and creating stars. Let's understand what makes this moment special, and then we'll follow the long, slow, inevitable path toward darkness. Let's see what happens when the Milky Way finally runs out of light. Right now, at this very moment, as you're reading or listening to these words, the Milky Way is doing something extraordinary. It's creating. Not metaphorically, not in some abstract sense, but literally, physically creating new stars. It's taking the simplest, most common stuff in the universe, hydrogen and helium, raw cosmic ingredients left over from the Big Bang 13.8 billion years ago, and it's turning them into suns, into massive thermonuclear furnaces that will burn for millions or billions or even trillions of years, depending on their size, into sources of light and heat that make planets warm enough for water to exist as a liquid, warm enough for complex chemistry to happen, warm enough for life to maybe emerge and evolve. This process of star formation is happening constantly, right now, this very second. Somewhere in our galaxy, at this exact moment, a cloud of hydrogen gas is collapsing under its own gravity. Atoms are being pulled together, drawn closer by the invisible hand of gravity, compressed into a smaller and smaller volume. As they compress, they speed up, they collide more often. The cloud heats up, the temperature rises, thousands of degrees, tens of thousands. And somewhere, right now, in some stellar nursery hidden behind veils of cosmic dust, a protostar is forming. A hot, glowing ball of gas that's not quite a star yet, but will be soon. It's still collapsing, still heating up, still compressing. The temperature at its core is climbing. 1,000,000 degrees, 5 million, 10 million, and somewhere, right now, maybe even in the moment between when I wrote this sentence and when you read it, a star is being born. The core temperature has reached the critical threshold of about 10 million degrees Celsius. At this temperature, hydrogen nuclei, which are just single protons, are moving so fast that they can overcome their electrical repulsion. Remember, protons are positively charged and, like charges, repel each other. Under normal circumstances, two protons would never get close enough to interact. But at 10 million degrees, these protons are moving at a significant fraction of the speed of light. When they collide, occasionally, rarely, but often enough, they get close enough for the strong nuclear force to take over. And when that happens, they stick together, they fuse. 4 hydrogen nuclei, through a complex series of reactions, fuse together to form 1 helium nucleus. And in that process, a tiny amount of mass is converted into energy according to Einstein's famous equation, E equals mc squared. That tiny amount of mass, about 0.7% of the original hydrogen mass, becomes energy, and because c, the speed of light, is such a large number, and because we're squaring it, that tiny amount of mass becomes an enormous amount of energy. When that first fusion reaction occurs in the core of a collapsing gas cloud, everything changes. The protostar becomes a true star. Energy begins pouring out from the core, radiating outward, creating pressure that pushes back against gravity. The collapse stops. The star reaches equilibrium. Gravity pulling inward is balanced by pressure pushing outward. And it will maintain this balance for its entire life, fusing hydrogen into helium, generating energy, pumping light and heat out into the cosmos. Our sun is doing this right now, has been doing it for 4.6 billion years, will continue doing it for another 5 billion years or so. Every second, the sun converts about 600 million tons of hydrogen into helium. 600 million tons every single second, and in that process, about 4 million tons of matter is converted into pure energy. 4 million tons of matter just vanishing, turning into light and heat and radiation that spreads out into space at the speed of light. Some of that energy, a tiny fraction of it, happens to hit Earth 8 minutes later after traveling 93 million miles through the vacuum of space. And that energy, those photons created in the sun's core through fusion, eventually radiated from the surface, traveling through space, passing through our atmosphere, landing on your skin. That energy makes life possible. It warms the planet. It drives weather. It powers photosynthesis in plants, which creates the oxygen you're breathing right now, which produces the food you eat. Everything alive on Earth, including you, is powered by fusion happening in the core of the sun. You are solar powered. You're running on starlight. And what's true for the sun is true for billions of other stars throughout the Milky Way. Each one a fusion reactor. Each one converting mass into energy. Each one pumping out light and heat. The Milky Way creates somewhere between 3 and 7 new stars every single year, depending on which estimates you believe and which measurements you trust. Let that sink in for a moment. 3 to 7 new suns every year. While you were reading the last few paragraphs, while we've been talking about star formation, there's a decent chance that somewhere in our galaxy, another star just ignited for the first time. Another nuclear furnace just turned on. Another source of light just began its long journey through the cosmos. And this has been happening continuously, without pause, without break, for over 13 billion years. Think about that. 13 billion years of constant star formation. That's more than twice as old as our solar system. That's almost as old as the universe itself. The Milky Way has been making stars since shortly after the Big Bang, since the first generation of stars enriched the cosmos with heavy elements, since galaxies first began to form from the lumpy distribution of dark matter left over from the early universe. 13 billion years is a number we can write down easily enough. But try to comprehend it. Try to really understand what that means. If each year of the Milky Way's history was 1 second, the galaxy would have been making stars for over 400 years. That's longer than the United States has existed. That's longer than most modern nations have existed. That's back to the Renaissance, to the Age of Exploration, to Columbus and Magellan, and the discovery that the Earth is round and not the center of everything. Every one of those seconds represents a year. A full year of star formation, a full year of new stars being born, a full year of light spreading through the galaxy. And this has happened not once, not 100 times, not 1,000 times, but billions of times. The scale is almost impossible to grasp, and the result is what we see when we look at the Milky Way from a dark location on a clear night. That band of light stretching across the sky, that foggy, milky appearance that gave our galaxy its name. That's not fog, that's not mist, that's not clouds, that's stars. Billions upon billions of stars, so many and so distant that they blur together into a continuous glow, each one a sun, each one potentially hosting planets, each one a story of stellar birth and life and eventual death. When you look at the Milky Way, you're looking at the cumulative result of 13 billion years of star formation. You're seeing our galaxy's history written in light. The young blue stars in the spiral arms, hot and bright and short-lived. The ancient red giants, stars like our sun that have exhausted their hydrogen cores and swelled up to enormous sizes as they begin to die. The yellow stars like our sun in their middle age, stable and steady, pumping out energy at a consistent rate year after year. The dim red dwarfs, so faint we can't see them without telescopes, but so numerous they make up the majority of all stars. And so long-lived they'll still be burning when everything else has gone dark. All of these stars, all of this light, all of this cosmic architecture exists because of star formation, because the Milky Way has a supply of hydrogen gas that it can turn into stars. And this is what makes our current moment, our current era, our current cosmic epoch special. We're living during the stelliferous era, the age of stars, the time when the universe is actively making stars, when galaxies are bright and dynamic, when new light is constantly being created. The stelliferous era began about 100 million to 300 million years after the Big Bang, when the first stars ignited in the primordial universe. Before that, during what astronomers call the cosmic dark ages, the universe was literally dark. There were no stars, no galaxies, no light except the gradually fading afterglow of the Big Bang itself. Just hydrogen and helium gas spread throughout space, slowly clumping together under gravity, forming structures that would eventually become galaxies and clusters of galaxies. But then, in those first clouds of gas, in the densest regions where gravity was strongest, the first stars ignited. Population 3 stars, astronomers call them, though none have ever been observed directly because they existed so long ago. These first stars were different from anything we see today. They were massive, probably 100 or even several hundred times the mass of our sun. They were made purely of hydrogen and helium because heavier elements didn't exist yet. They burned incredibly hot and bright, pouring out ultraviolet radiation that began to ionize the surrounding gas, creating bubbles of ionized gas that grew and eventually overlapped, reionizing the entire universe. This period is called the Epoch of Reionization, and it marked the end of the Dark Ages and the beginning of the Stelliferous Era. But these first stars were also short-lived. A star with 100 times the mass of the Sun burns through its fuel in just a few million years. Compare that to the Sun's 10 billion year lifespan, or to the smallest red dwarfs that can burn for 10 trillion years. And you see how fleeting these first stars were, but their deaths were crucial. When a massive star runs out of hydrogen, it doesn't just fade away quietly. It undergoes a series of increasingly rapid fusion reactions, fusing helium into carbon and oxygen, carbon into neon and magnesium, oxygen into silicon and sulfur, silicon into iron. Each stage produces less energy and lasts less time than the one before. The final stage, silicon fusion creating iron in the core, lasts only a few days. And then it's over. Iron won't fuse. It's at the bottom of the nuclear binding energy curve. Fusing it would require energy input rather than releasing energy. So, when the core becomes iron, there's no more fusion to provide pressure against gravity. The core collapses, catastrophically. In less than a second, the core implodes to a fraction of its original size, releasing more energy than the star has produced in its entire lifetime. The collapse is so violent that it rebounds, sending a shock wave out through the star's outer layers. The star explodes, a supernova. For a few weeks, this single dying star can outshine an entire galaxy, and, crucially, this explosion scatters the star's enriched material into space. All those heavy elements created through fusion, carbon and nitrogen and oxygen and silicon and iron and everything else, plus even heavier elements created in the explosion itself through rapid neutron capture, all of it gets injected into the interstellar medium. The first generation of supernovae seeded the universe with heavy elements for the first time. And when the next generation of stars formed from this enriched gas, they contained these elements. Stars that formed from this second generation gas could be smaller because the heavy elements allowed the gas to cool more efficiently during collapse. They could form planetary systems with rocky planets, not just gas giants, because now there were elements heavier than hydrogen and helium to make rock from. Generation after generation continued this process, each cycle enriching the interstellar medium further, each cycle making the next generation more like the stars we see today, more capable of hosting planets like Earth, more conducive to the eventual emergence of life. Our Sun is a third-generation star, maybe even fourth or fifth generation depending on how you count. It formed about 4.6 billion years ago from a cloud of gas that had been enriched by multiple previous generations of stars. The heavy elements in that cloud, the carbon and oxygen and nitrogen and iron, all of it came from stars that lived and died before our Sun existed. And those heavy elements made our solar system possible. They made rocky planets like Earth possible. They made oceans possible. They made life possible. And eventually, billions of years later, they made you possible. The calcium in your bones came from an exploding star. The iron in your blood came from an exploding star. The carbon that forms the backbone of every organic molecule in your body came from fusion inside a star that died before our Sun was born. You are literally made of stardust. This isn't poetry, it's fact. Every atom heavier than hydrogen in your body was created inside a star. You are the universe's way of understanding itself. You are the product of billions of years of cosmic evolution, of star formation and death and rebirth, of matter gradually organizing itself into increasingly complex structures until finally, somehow, some of that matter became conscious and could contemplate its own origins. And all of this happened during the Stelliferous era, during the time when stars are forming and enriching the cosmos with heavy elements and making complexity possible. This era, this age we're living in right now, is special. It's not going to last forever, and that's what we need to talk about next. Because while the stelliferous era seems eternal from our perspective, while it's already lasted for over 13 billion years and will continue for trillions more, it is finite. It has a beginning and it will have an end. Star formation requires fuel, it requires hydrogen gas, and the amount of hydrogen available to make stars is limited. Not small, not running out tomorrow, but finite. Eventually, inevitably, the Milky Way will run out of hydrogen to turn into stars. And when that happens, when the last new star finally ignites, the galaxy enters a new phase, a phase where it must survive on the stars it's already made, watching them slowly, one by one, burn out and die. But before we get to that distant future, before we watch the slow dimming and death of the galaxy, there's something else that's going to happen. Something dramatic, something that will completely reshape the Milky Way as we know it, something that's already in progress, already happening right now, even though we can't see it with our eyes. In about 4 billion years, give or take a few 100 million, the Milky Way is going to collide with our nearest large neighbor, the Andromeda Galaxy. This collision is inevitable. It's not a maybe or a possibly, it's a certainty, as sure as the fact that the sun will rise tomorrow, as guaranteed as the law of gravity. Andromeda is coming, and there's nothing that can stop it. Right now, as you're reading this, Andromeda is hurtling toward us at about 400,000 kilometers per hour. That's roughly 112 kilometers per second. If you could somehow get in a spaceship and travel at highway speeds, about 100 kilometers per hour, it would take you about 25 million years of continuous driving to cover the distance that Andromeda is covering every single hour. The galaxy is moving fast, incredibly fast by human standards, and it's moving directly toward us, pulled by the mutual gravitational attraction between our two galaxies. From Earth, Andromeda appears as a faint, fuzzy patch in the night sky. On a really dark night, far from city lights, you can see it with your naked eye. It's about 2.5 million light years away, which means the light you're seeing left Andromeda 2.5 million years ago. When those photons began their journey toward Earth, our ancestors were just learning to use stone tools. They were Homo habilis, maybe early Homo erectus. They walked upright, but their brains were smaller than ours. They hadn't developed language yet. They hadn't discovered fire. They were living in Africa, competing with other predators, trying to survive long enough to reproduce. And while they were doing all of that, while our ancestors were slowly, gradually evolving toward modern humans, light from Andromeda was traveling through space, crossing the 2.5 million light years that separate our galaxies. Traveling at 300,000 kilometers per second, the fastest speed possible in the universe, and still taking 2.5 million years to make the journey. That's how far away Andromeda is. That's the distance that separates us from our nearest large galactic neighbor. But that distance is shrinking. Every second, we get 112 kilometers closer. Every minute, about 6,700 kilometers closer. Every hour, about 400,000 kilometers closer. Every day, about 9.6 million kilometers closer. It doesn't sound like much compared to the vast distance that still separates us. But given enough time, given billions of years, Andromeda will arrive. And when it does, when these two massive collections of stars and gas and dark matter finally meet, something spectacular happens. Now, when I say the Milky Way and Andromeda are going to collide, I need to be very clear about what that actually means. Because it's not what most people picture when they hear the word collision. This isn't going to be like two cars crashing into each other. It's not going to be like two rocks smashing together. It's not even going to be like two water droplets merging, though that's closer to the truth. Galaxies are mostly empty space. Mostly. The word mostly is doing a lot of work in that sentence, but it's true. Think about our solar system. The Sun is about 1.4 million kilometers in diameter. That's huge, monumentally huge. You could fit over 100 Earths side by side across the Sun's diameter. But the distance from the Sun to the nearest star, Proxima Centauri, is about 40 trillion kilometers. That's roughly 30 million times farther than the Sun's diameter. If you imagine the Sun as a basketball, then the nearest star is another basketball about 5,000 kilometers away. That's roughly the distance from New York to London. Everything in between is empty space, and this is typical for our region of the galaxy. Stars are tiny compared to the vast distances separating them. There's an enormous amount of nothing between each star. So, when two galaxies collide, when the Milky Way and Andromeda finally meet, the stars themselves almost never actually hit each other. Almost never. It's not impossible, but it's incredibly unlikely. The odds of any two stars actually colliding during a galactic merger are astronomically small. Most stars will pass by each other like dancers moving through a crowded ballroom. Close sometimes, close enough to gravitationally affect each other's trajectories, but not actually touching, not actually colliding. So, if the stars don't hit each other, what does collide? The answer is the galaxies as structures. Their overall shapes deform. Their spiral arms get stretched and twisted by tidal forces. The gas clouds that fill the space between stars, the diffuse interstellar medium, those clouds do collide. When gas from one galaxy meets gas from another galaxy, they don't just pass through each other, they slam together. They create shock waves. They compress, and when gas compresses, it heats up, and when it heats up and then cools down, it can collapse more readily, which means galactic collisions trigger star formation, massive bursts of star formation. Some of the brightest, most active galaxies we observe in the universe are galaxies currently undergoing mergers. The collision compresses their gas, triggering enormous waves of star formation, creating thousands or even millions of new stars in a relatively short time. Our collision with Andromeda will do the same thing. When our two galaxies meet, when our gas clouds collide and compress, the Milky Way will experience bursts of star formation more intense than anything it's seen in billions of years. Stellar nurseries will light up throughout the merged system. New stars will form at rates far higher than the current 3 to 7 per year. For a while, for a few 100 million years perhaps, the merged galaxy will be brighter and more active than either of its parent galaxies were separately. The collision doesn't happen all at once. It's not a single crash. It's a slow motion dance that plays out over billions of years. The first close passage occurs about 3.7 billion years from now, according to current models based on observations of Andromeda's trajectory. At this point, the two galaxies are still distinct. They haven't merged yet, but they're close enough that their mutual gravity is affecting each other strongly. The spiral arms, those beautiful, graceful curves that give both galaxies their characteristic appearance, start to distort. Stars in the outer regions of both galaxies get pulled toward the other galaxy. Some get captured, switching allegiance from one galaxy to the other. Others get flung outward into intergalactic space by the complex gravitational interactions, exiled from both galaxies, doomed to drift alone through the void. Long tidal tails form. These are streams of stars pulled out of the galaxies by tidal forces, similar to how the moon creates tides on Earth, but on an incomparably larger scale. These tidal tails can extend for hundreds of thousands of light years, creating vast cosmic structures that dwarf anything we see in either galaxy today. We actually observe galaxies undergoing mergers throughout the universe, and many of them have these spectacular tidal tails. Long arcs and streams of stars stretching out into space, marking the gravitational violence of the collision. After that first close pass, the two galaxies swing away from each other. But they don't escape. They're gravitationally bound. They're locked in an embrace they can't break. Over the next few billion years, they swing around, approaching each other again, passing close again. Each passage pulls more stars out of their original galaxies. Each passage triggers more bursts of star formation. Each passage brings the two galaxies closer to their final merger. Eventually, after several close passages over a period of perhaps 2 to 3 billion years, the two galaxies fully merge. Their stellar populations intermix. Their gas clouds combine. The beautiful spiral structures that characterized both galaxies are destroyed, scrambled by the gravitational chaos of the merger. What emerges is something different. An elliptical galaxy, a galaxy with no spiral arms, no organized structure, just a smooth distribution of stars in a roughly spherical or football-shaped configuration. Astronomers have already given this future galaxy a name: Milky Way, a portmanteau of Milky Way and Andromeda. Cute, right? A little on the nose, perhaps, but descriptive. Milky Way will be huge. It will contain all the stars from both parent galaxies, somewhere in the vicinity of 1 trillion stars total. That's more than twice as many as either galaxy has now. It will be one of the largest galaxies in our local group, the collection of gravitationally bound galaxies that includes the Milky Way, Andromeda, and about 50 smaller galaxies. But here's something crucial to understand. The merger doesn't fundamentally change the fate of the galaxy. It might accelerate some things, it might delay others, but the ultimate end result is the same. Milky Way, like the Milky Way before it, like Andromeda before it, like every galaxy in the universe, is running on a finite supply of hydrogen fuel. The collision might trigger massive bursts of star formation that use up a significant fraction of the remaining gas. Or the collision might compress gas in ways that make future star formation more efficient for a while. But either way, the gas is finite. Eventually, it runs out. Eventually, star formation slows and then stops. Eventually, all the stars that can form have formed, and all that remains is to wait for them to die. The merger might shift the timeline by a few billion years one way or another, but it doesn't change the destination. Milky Way will follow the same path as every other galaxy. It will age, it will consume its resources, it will dim, and eventually it will die. But I'm getting ahead of myself. Before we watch the death of the stars, before we follow Milky Way into the degenerate era and beyond, we need to talk about what happens to our solar system during all of this. Because while all of this galactic drama is playing out, while the Milky Way and Andromeda are dancing and merging and forming Milky Way, our sun and planets are along for the ride. And some very significant things are happening to them during this time. By the time the collision really gets going, by the time we're approaching that first close pass about 3.7 billion years from now, our sun will be noticeably different from how it is today. It will be brighter, about 20% brighter than it is right now. This might not sound like much. 20% is significant, but not dramatic, right? You probably wouldn't notice if your lights at home got 20% brighter. But when we're talking about the sun, when we're talking about the source of essentially all energy for life on Earth, 20% makes a huge difference. The sun has been slowly getting brighter throughout its entire life. This is a natural consequence of how stellar fusion works. The sun fuses hydrogen into helium in its core. As it does this, helium accumulates. Helium is denser than hydrogen, so as the core fills up with helium, it becomes denser. This increased density allows the core to compress further under gravity. The compression makes it hotter. The higher temperature makes fusion proceed faster, which produces more energy, which makes the sun brighter. It's a feedback loop. The sun gets gradually brighter as it ages. When the sun formed 4.6 billion years ago, it was about 30% dimmer than it is today. If you could somehow go back in time and replace today's sun with the young sun, Earth would freeze. Our planet is in the habitable zone now, at the right distance for liquid water to exist, partly because of how bright the sun is now. If the sun were 30% dimmer, Earth would be too cold for liquid water. The oceans would freeze solid. Life as we know it couldn't exist. This is actually a puzzle that planetary scientists call the faint young sun paradox. We have geological evidence that liquid water existed on Earth's surface over 3.5 billion years ago, maybe even 4 billion years ago. But the sun was dimmer back then, so Earth should have been frozen. The solution is probably that Earth's atmosphere was different, containing more greenhouse gases that trapped more heat, compensating for the dimmer sun. As the sun brightened over billions of years, the atmosphere gradually changed, maintaining a relatively stable surface temperature. But this balancing act can't continue forever. Eventually, the sun will be too bright for Earth to remain habitable, and this is already starting to happen on geological timescales. In about 1 billion years from now, long before the Milky Way and Andromeda actually collide, the sun will be about 10% brighter than it is today. That 10% increase will be enough to trigger a runaway greenhouse effect on Earth. Let me explain what that means and why it's so devastating. Water vapor is a greenhouse gas. It traps heat in the atmosphere. Right now, Earth has a stable water cycle. Water evaporates from the oceans, forms clouds, falls as rain or snow, flows back to the oceans. It's a cycle, a balance. But if the temperature increases enough, more water evaporates. More water vapor in the atmosphere means more heat gets trapped, which raises the temperature further, which causes more water to evaporate. See the problem? It's a positive feedback loop. Once it starts, it accelerates. The hotter it gets, the more water evaporates. The more water evaporates, the hotter it gets. And there's no natural break on this process once it begins. In about 1 billion years, the sun's increased brightness will push Earth over this threshold. The oceans will begin to evaporate, not all at once, not overnight, but gradually over millions of years. The water that currently covers 70% of Earth's surface will be transformed into atmospheric water vapor. The atmosphere will become thick with steam. The surface temperature will climb higher and higher, hundreds of degrees. Eventually, the atmosphere will be so hot and so full of water vapor that water can no longer exist as a liquid on the surface. All of Earth's water will either be in the atmosphere as vapor or will have been broken apart by ultraviolet radiation from the sun, with the hydrogen escaping into space and the oxygen reacting with rocks on the surface. Earth will become Venus, a scorched hothouse planet with surface temperatures hot enough to melt lead. No oceans, no rain, no water cycle, no life as we know it. This is Earth's fate about 1 billion years from now, long before the Milky Way and Andromeda actually collide, long before the formation of Milky Way. The sun's gradual brightening, the same process that's been happening since the sun formed, the same process that's kept Earth habitable for billions of years, will eventually make Earth uninhabitable. If anyone is still on Earth at this time, they won't be human, not in any sense we would recognize. 1 billion years is enough time for evolution to transform a species beyond recognition multiple times over. If intelligence persists, if consciousness continues, the beings that exist then will be so different from us that we might not even recognize them as our descendants. Or perhaps by then, intelligence will have left Earth entirely. Perhaps will have spread to other worlds, to other star systems, carrying life and consciousness to new homes before Earth becomes uninhabitable. Perhaps our descendants will look back at Earth from distant colonies and watch sadly as their ancestral home transforms into a dead, waterless desert under an increasingly bright sun. Or perhaps consciousness won't survive that long. Perhaps we'll destroy ourselves long before the sun does the job for us. Perhaps we're living through one of the brief windows when intelligent life can exist, and we'll squander it before we can spread beyond our home planet. We don't know. We can't know. But we do know what will happen to Earth. We know what will happen to the sun, because the physics is clear. The math is straightforward. The fate is inevitable. After Earth's oceans boil away, after the planet becomes uninhabitable, the sun will continue brightening. By about 5 billion years from now, about the same time as the Milky Way and Andromeda are in the final stages of their merger, the sun will have exhausted the hydrogen in its core. For 4.5 billion years up to that point, for 9 billion years total, the sun will have been fusing hydrogen into helium in its core. But eventually, the hydrogen runs out. And when it does, fusion stops in the core. Without fusion generating energy, there's nothing to push back against gravity. The core begins to contract, but here's where it gets interesting. As the core contracts, it heats up, just like the original gas cloud that formed the sun heated up as it collapsed. The contracting core gets hotter, and even though there's no more hydrogen in the core to fuse, there's still hydrogen in a shell around the core, and as the core contracts and heats up, it heats this shell. Eventually, the shell gets hot enough for hydrogen fusion to begin there. So now the sun is fusing hydrogen in a shell around an inert helium core. This shell fusion is actually more energetic than the core fusion was. It produces more energy, which makes the sun's outer layers expand dramatically. The sun swells up. It becomes a red giant. Over the course of a few 100 million years, the sun's radius will increase by a factor of about 250. It will grow so large that it will engulf the inner planets. Mercury will definitely be swallowed. Venus almost certainly. Earth is right on the edge. Some models suggest Earth will be consumed by the expanding sun. Others suggest it will just barely avoid being swallowed, but will be left as a scorched, airless rock orbiting just outside the sun's surface. Either way, Earth as we know it is gone. If it's swallowed, it vaporizes in the sun's outer atmosphere. If it survives, it's a dead world, too close to the sun to ever support life again. And all of this is happening during the same time period when the Milky Way and Andromeda are merging. While these galactic giants are dancing around each other, triggering bursts of star formation, mixing their stellar populations, our own sun is dying. Our home star is swelling into a red giant, destroying the inner planets, transforming itself into something unrecognizable. If there are any observers at this time, any consciousnesses that have persisted or evolved or been created in the billions of years since now, they would see something extraordinary. If they're located far enough from the sun to be safe, perhaps in the outer solar system, perhaps having migrated to the moons of Jupiter or Saturn, they would look up and see a sky utterly transformed. First, they would see the sun, but it wouldn't look like the sun we know. It would be enormous. A bloated red giant filling a huge portion of the sky. From Earth's orbit, if Earth still exists, the sun would appear about 200 times larger than it does today. It would cover a significant fraction of the visible sky, and it would be red. Not the warm yellow-white we're used to, but a deep, ominous red, the color of a dying star. But that's not all they would see, because this is also the time when Andromeda and the Milky Way are merging. The night sky would be unrecognizable compared to what we see today. Instead of a few thousand stars visible to the naked eye, there would be hundreds of thousands, maybe millions. Stars from both galaxies intermixed, creating a sky far denser with stars than anything humans have ever seen. The Milky Way as we know it, that band of light stretching across the sky, would be gone, replaced by a more uniform distribution of stars in every direction. The beautiful spiral structure visible in photographs of our galaxy would be destroyed, scrambled by the gravitational chaos of the merger. And if they looked carefully, if they had telescopes or enhanced vision, they would see evidence of the collision everywhere. long streamers of stars stretching across the sky, tidal tails pulled out by gravitational interactions. Bright knots of star formation where gas clouds have collided and compressed, creating thousands of new stars in regions that were once dark. The glow from the galactic center would be brighter than ever as gas funnels into the merged supermassive black hole at the center of Milky Way, heating up and emitting intense radiation before falling past the point of no return. It would be a sky of wonders, a sky that would make our current night sky look dim and empty by comparison. But it would also be a sky of endings. The sun dying, Earth gone or uninhabitable, the Milky Way as a distinct galaxy ceasing to exist. Everything changing, everything transforming, everything moving toward the inevitable conclusion that we're building toward in this journey. The slow dimming, the gradual fade, the end of the age of stars. But let's focus on the sun for a moment longer, because its story isn't over yet. The red giant phase lasts for about 1 billion years. During this time, the sun is fusing hydrogen in a shell around its inert helium core. The core continues to contract and heat up under gravity. Eventually, after about 1 billion years of shell fusion, the core gets hot enough for helium to fuse. At about 100 million degrees Celsius, helium nuclei can overcome their mutual repulsion and fuse together. 3 helium nuclei fuse to form 1 carbon nucleus in a process called the triple alpha process. This is a delicate reaction. It requires 3 helium nuclei to collide nearly simultaneously, which is unlikely. But in the incredibly dense, incredibly hot core of a red giant, it happens often enough to generate significant energy. When helium fusion begins in the sun's core, something dramatic occurs. For a brief time, a few minutes to a few hours depending on the exact conditions, the core is unstable. Energy generation increases rapidly. The core heats up, which increases the fusion rate, which generates more energy. It's a runaway process. Astronomers call this the helium flash. It's not visible from outside the star because it happens deep in the core, buried under enormous amounts of stellar material. But it's a significant event in the star's evolution. After the helium flash, the core settles into a new equilibrium. Now it's fusing helium into carbon in the core, while still fusing hydrogen in a shell around the core. The sun enters a phase called the horizontal branch, a technical term referring to where these stars appear on a diagram plotting stellar luminosity against temperature. For a few 100 million years, the sun burns relatively stable in this configuration. But eventually, the helium in the core runs out, and when it does, fusion stops in the core again. The core, now made of carbon and oxygen, begins to contract. The shell fusion continues, both hydrogen and helium burning in shells around the inert carbon-oxygen core. The sun enters what's called the asymptotic giant branch. It swells even larger than it did during the first red giant phase. It becomes unstable. Every few thousand years, it experiences thermal pulses where the fusion shells briefly increase their energy output, causing the star's outer layers to expand and then contract again. And during these pulses, the sun begins to shed its outer layers. Material from the outer envelope is blown off into space by radiation pressure and stellar winds. The sun is literally tearing itself apart. Gradually, over tens of thousands of years, the entire hydrogen and helium envelope is ejected. This material spreads out around the dying star, creating a planetary nebula, a shell of glowing gas expanding into space. These nebulae are some of the most beautiful objects in astronomy. The Ring Nebula, the Helix Nebula, the Dumbbell Nebula. They're all formed by sun-like stars in their final death throes, ejecting their outer layers as they die. Our sun will create such a nebula about 7 billion years from now. Future observers, if any exist, if any have survived the death of Earth and the transformation of the solar system, will see this glowing shell of gas expanding outward from what used to be our sun. And at the center, where the sun used to be, there will be something new, something small and incredibly dense. A white dwarf. This is what's left of the sun's core. All that remains after the outer layers have been ejected. It's about the size of Earth, but with about half the sun's mass compressed into that small volume. It's incredibly dense. A teaspoon of white dwarf material would weigh about 15 tons on Earth. It's also incredibly hot initially, over 100,000 degrees at the surface, hot enough to glow blue-white. But here's the crucial thing. A white dwarf has no energy source. Fusion has stopped completely. The core isn't hot enough or dense enough to fuse carbon and oxygen. Only the most massive stars can do that. For a star like the Sun, this is the end of the line. No more fusion, no more energy generation. The white dwarf is just cooling off, radiating its heat into space, getting dimmer and cooler as the eons pass. It will take trillions of years for the white dwarf to cool completely, far longer than the current age of the universe. But it will happen eventually. Given enough time, the white dwarf will fade to a black dwarf. A cold, dark sphere of carbon and oxygen no longer emitting any detectable radiation, just a stellar corpse drifting through space, invisible except for its gravitational influence. This is the fate of our sun. This is the fate of every star similar to the sun. Every star between about half a solar mass and about 8 solar masses. They all follow this same path. Main sequence star, red giant, helium core fusion, asymptotic giant branch, planetary nebula, white dwarf, black dwarf. It's a timeline measured in billions and trillions of years, but it's the same basic process for all of them. And by the time our sun reaches the white dwarf stage, by the time it's a cooling stellar corpse about 7 billion years from now, the merger of the Milky Way and Andromeda will be complete. Milkomeda will have settled into its new configuration as a giant elliptical galaxy. The bursts of star formation triggered by the collision will have subsided. The galaxy will have used up a significant fraction of its remaining hydrogen gas, creating new stars during the merger, and it will be entering a new, quieter phase, a phase where star formation continues, but at a much lower rate than during the collision, a phase where the galaxy is beginning its long, slow decline, beginning the gradual dimming that will eventually lead to the complete death of all stars. And this is where we start to see the end approaching. Not the immediate end, not tomorrow or next year or even in the next few billion years, but the beginning of the end. The first signs that the stelliferous era, the age of stars that's defined the universe for over 13 billion years, is starting to wind down. Star formation in Milky Way will continue for tens of billions of years after the merger, maybe even 100 billion years or more, but it will be slowing down. The rate of new star formation will gradually decrease as the available hydrogen gas gets used up, and, crucially, no new gas is coming in. In the early universe, galaxies were constantly fed by streams of fresh gas flowing in from the cosmic web, the large-scale structure of dark matter and intergalactic gas. But as the universe expands and ages, these streams weaken. The gas gets more diffuse, more distant. By the time we reach Milky Way's formation, 7 or 8 billion years from now, these streams have mostly dried up. Milky Way is essentially cut off. It's on its own. It has to survive on the gas it already contains, and that gas is finite. Every new star that forms locks away hydrogen. Some of that hydrogen gets converted to helium and eventually to heavier elements through fusion. Some gets locked in long-lived stars like red dwarfs that will burn for trillions of years. Some gets blown out of the galaxy entirely by supernovae and stellar winds, expelled into intergalactic space where it won't come back. The reservoir is depleting, slowly, very slowly, but inexorably. By about 50 billion years after the Big Bang, about 35 billion years from now, star formation in Milky Way will have slowed to a trickle. The bright blue stars, the massive ones that live fast and die young, will be gone. No more are being created. The medium-sized stars like our Sun will mostly be gone too, either dead as white dwarfs or in their final red giant phases. What remains are the long-lived stars. The red dwarfs, stars with masses less than about half that of the Sun, burning their hydrogen so slowly and carefully that they can keep going for timescales that dwarf everything we've talked about so far. The smallest red dwarfs, with masses around 8 to 10% of the Sun's mass, can burn for 10 trillion years. 10,000 billion years. That's about 700 times longer than the current age of the universe. That's long enough for the universe to go through massive changes. Long enough for dark energy to have a profound effect on cosmic expansion. Long enough for galaxies outside our local group to be carried so far away by the expansion of space that they disappear beyond the cosmic horizon and become forever unreachable and unobservable. These red dwarfs will be the last stars burning, the final lights in the galaxy. By about 100 billion years after the Big Bang, the last new star will have formed in Milky Way. The very last time a cloud of gas will collapse and ignite fusion, creating a new sun. After that, there are no more. The hydrogen is gone, all of it either locked up in existing stars, converted to heavier elements, or expelled from the galaxy. Star formation has ceased, and this marks the end of the stelliferous era for Milky Way, the end of the age of star creation. But the galaxy doesn't immediately go dark. Not even close, because all those stars that have already formed, all those billions or trillions of red dwarfs still burning, they'll continue for trillions of years more. The galaxy will dim. But slowly, so incredibly slowly, that you could watch for millions of years and barely notice the difference. The transition from the stelliferous era to the degenerate era isn't a sharp boundary. It's a gradual shift that plays out over timescales longer than the entire history of the universe up to this point. But it's real. It's happening. And once it begins, once that last star forms and no more will ever form again, the direction is set. The galaxy is on a one-way path toward darkness, toward the end of all light, toward the heat, death that awaits everything. We've traveled from the present moment, from our current cosmic epoch in the middle of the stelliferous era, through the collision of the Milky Way and Andromeda, through the death of our Sun and the transformation of Earth, through the formation of Milky Way and the gradual slowing of star formation, all the way to the end of the stelliferous era about 100 billion years from now. We've covered a span of time longer than the universe has currently existed. We've witnessed events that will reshape our cosmic neighborhood beyond recognition. But we're only halfway through this journey, because what comes next, what happens after the last star forms, is even stranger, even more profound, even more challenging to comprehend. So here we are, 100 billion years after the Big Bang. The last new star in Milky Way has just ignited. It's probably a small red dwarf, one of those miserly little stars that burns its fuel so carefully it could last for 10 trillion years. But it's the last one. After this, no more stars will ever form in what used to be the Milky Way. The hydrogen is gone, all of it locked up in existing stars, converted to heavier elements through fusion, or expelled from the galaxy entirely. The stellar nurseries that have been creating new suns for over 100 billion years have gone silent. The clouds of gas and dust that used to collapse into protostars have been consumed. The era of creation is over. But if you could somehow observe Milky Way from a distance at this moment, you wouldn't notice much difference from how it looked 10 billion years earlier. The galaxy would still be glowing, still full of stars, still radiating light into the cosmos. Because star formation ending doesn't mean the stars immediately disappear. It just means no new ones are being added. The existing stars continue burning, continue shining, continue pumping out energy. And there are a lot of existing stars, trillions of them. The vast majority are red dwarfs, those small dim stars that make up about 70 to 80% of all stars in the galaxy. And these red dwarfs will keep burning for timescales that make the entire history of the universe up to this point seem like a brief moment. Let me help you understand just how long-lived these stars are. The smallest red dwarfs, with masses around 8 to 10% of the Sun's mass, can maintain hydrogen fusion for about 10 trillion years. Let me write that out. 10 trillion years. 10,000 billion years. That's about 700 times longer than the current age of the universe. If the universe's current age was 1 year, these red dwarfs would burn for 700 years. That's longer than the United States has existed. That's back to the Renaissance. That's longer than gunpowder has been used in warfare. That's how disproportionately long these stars live compared to everything that's happened so far. Why do they last so long? It comes down to how they burn their fuel. Massive stars, The big blue giants that outshine everything else burn through their hydrogen like there's no tomorrow. They're hot, they're bright, they're profligate with their fuel. A star with 100 times the mass of the Sun will exhaust its hydrogen in just a few million years. It burns bright and dies young. Medium-sized stars like our Sun are more conservative. They burn steadily for billions of years. The Sun will last about 10 billion years total on the main sequence, fusing hydrogen in its core. That's a long time by human standards, but nothing compared to red dwarfs. Red dwarfs are different. They're small, which means they have less mass. But crucially, they're also much cooler. Their cores are cooler than the Sun's core, and cooler temperatures mean fusion proceeds more slowly. The hydrogen burns, but at a much more sedate pace. Less energy is generated, which is why red dwarfs are so dim. But that lower energy generation rate means the fuel lasts much, much longer. There's another factor too. Red dwarfs are fully convective. This means that material from their outer layers circulates down to the core, and material from the core circulates out to the surface. The entire star is constantly mixing. In larger stars like the Sun, only the outer layers are convective. The core is separate. This means that only the hydrogen in the core can be burned. The hydrogen in the outer layers never gets hot enough to fuse. It's wasted fuel. But in red dwarfs, because the entire star mixes, all the hydrogen can eventually make its way to the core and be burned. A red dwarf can use essentially 100% of its hydrogen fuel. The Sun can only use about 10%. This combination of slow burning and efficient fuel use means red dwarfs can last for trillions of years. And during the early degenerate era, during the first few trillion years after star formation has ceased, these red dwarfs are the galaxy's primary source of light. They're dim. Each one is far less luminous than the Sun, but there are so many of them that collectively they keep the galaxy glowing. If you could watch Milky Way during this time, you'd see it gradually getting redder. The blue stars are long gone. The white and yellow stars like the Sun are mostly gone, dead as white dwarfs. What remains are the red dwarfs, giving the galaxy a deep red hue. It would look like a galaxy of embers, of dying coals, still glowing, still warm, but clearly in decline, clearly aging. The night sky from any surviving planet orbiting one of these red dwarfs would be strange and sparse. Far fewer stars would be visible than we see from Earth today. The nearest neighbors might be dozens or hundreds of light years away. The galaxy would feel emptier, more isolated, more vast, and the stars you could see would all be red. Dim red points of light scattered across a mostly dark sky. No bright blue stars to catch your eye. No brilliant white stars to serve as navigation points. Just red. Everywhere red. The color of old stars, the color of endings. But these stars are stable. They burn steadily, year after year, millennium after millennium, eon after eon. For trillions of years, they maintain fusion in their cores. For trillions of years, they provide light and heat to any planets that might orbit them. For trillions of years, they hold back the darkness. But eventually, inevitably, even these miserly little stars run out of fuel. It takes a long time, an incredibly long time. But it happens. The smallest red dwarfs, the ones that can burn for 10 trillion years, will be the last to go. But around 10 trillion years after the Big Bang, about 9.9 trillion years from now, the first of these long-lived red dwarfs will finally exhaust their hydrogen. And when they do, they don't explode. They don't swell into red giants like the Sun did. They're too small for that. They don't have enough mass. Instead, they just stop. The fusion shuts off. The core stops generating energy. Gravity begins to compress the star. But there's no shell fusion to make it expand into a giant. There's no helium flash because the core never gets hot enough to fuse helium. The star just contracts and cools, transitioning directly from a main sequence red dwarf to a white dwarf. A helium white dwarf, since that's what the core is made of after all the hydrogen has been converted. And then it begins the long, slow process of cooling off, radiating its heat into space, getting dimmer and cooler with each passing year. This is how the galaxy dies, not all at once, not in some dramatic event, but star by star. One red dwarf exhausts its fuel and shuts down, then another, then another. The process accelerates as we approach the point when most red dwarfs are reaching the end of their lives. For a while, for perhaps a few 100 billion years, red dwarfs are dying at a rate of maybe a few per year across the entire galaxy. It doesn't sound like much, but it adds up. Each one that dies makes the galaxy slightly dimmer. Each one that shuts down removes another source of light from the cosmos. And, crucially, no new stars are forming to replace them. Every death is permanent. Every star that goes out is gone forever. The galaxy grows dimmer, and dimmer, and dimmer still. By about 15 trillion years after the Big Bang, most of the red dwarfs have died. The galaxy is now much darker than it was, much quieter, much emptier feeling. The remaining red dwarfs, the very smallest and longest-lived ones, continue burning. But they're few and far between, scattered across the vast volume of the galaxy, islands of light in an increasingly dark sea. And then, around 20 trillion years after the Big Bang, the last red dwarf in Milky Way finally exhausts its hydrogen fuel. For the first time in about 20 trillion years, since the first stars formed shortly after the Big Bang, there is no star in the galaxy fusing hydrogen. The main sequence is over, completely over. Every star that could burn hydrogen has burned hydrogen and stopped. What remains is a galaxy of corpses, of stellar remnants, of objects that used to be stars but aren't anymore. White dwarfs cooling slowly in the darkness, brown dwarfs, objects that never quite had enough mass to ignite fusion in the first place, now just cold balls of hydrogen slowly contracting and cooling. Neutron stars, the ultra-dense cores left behind by supernovae, spinning silently in the void. And black holes, scattered throughout the galaxy, invisible, detectable only through their gravitational influence on nearby objects. This is the Middle Degenerate Era, the age of stellar remnants, and it's going to last far longer than the Stelliferous Era did, far longer than the time of burning stars. Because while the stars lived for billions or trillions of years, the remnants they left behind can persist for quadrillions of years or more. White dwarfs, in particular, are incredibly long-lived. They start out hot, very hot. When the sun becomes a white dwarf, its surface temperature will be over 100,000 degrees Celsius. That's about 17 times hotter than the sun's surface is now. At that temperature, a white dwarf glows blue-white. It's actually brighter per unit surface area than the sun is now, but it's much smaller, only about the size of Earth, so its total luminosity is much less than the sun's current luminosity. Still, a young white dwarf is a respectable source of light. If you had a planet orbiting in the right location close enough to receive adequate warmth, the white dwarf could keep that planet habitable. But here's the thing. A white dwarf has no energy source. Fusion stopped long ago. All the white dwarf can do is radiate away its stored thermal energy. It's like a hot stove that's been turned off. It starts out hot, but it gradually cools as it radiates heat into the surrounding space. And because a white dwarf is so dense, because it has about half the mass of the sun compressed into a volume the size of Earth, it has a lot of thermal energy to radiate. It takes a long time to cool down. How long? Well, that depends on the mass of the white dwarf, but for a typical one, it takes about 100 million years to cool from 100,000 degrees to about 25,000 degrees. At 25,000 degrees, it's still incredibly hot by any normal standard, but it's noticeably cooler than when it started. It's moved from blue-white to white in color. The cooling continues. After about 1 billion years, the white dwarf has cooled to about 8,000 degrees. Still hot, still glowing white or slightly yellowish, but definitely cooling. After about 10 billion years, it's down to about 5,000 degrees, about the same temperature as the sun's surface is now. It glows yellow. After 100 billion years, it's cooled to maybe 3,000 degrees. It glows orange or red. It's much dimmer now, much less luminous, but it's still radiating, still visible. The cooling process slows as the white dwarf gets cooler. This is because the rate of cooling depends on the temperature. The hotter an object is, the faster it radiates energy. As the white dwarf cools, its cooling rate decreases. It takes longer and longer for each additional drop in temperature. By 1 trillion years, the white dwarf might be around 1,000 degrees. It's now a deep red, barely glowing. By 10 trillion years, it might be down to a few hundred degrees. It's becoming infrared, no longer visible to the eye, but still radiating in the infrared part of the spectrum, still emitting photons, still technically glowing. And this continues for timescales that are hard to even write down. Quadrillions of years. Quintillions of years. The white dwarf continues to cool, asymptotically approaching absolute zero, but never quite reaching it. Eventually, after about 100 quintillion years, give or take an order of magnitude, the white dwarf has cooled to essentially the temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. At this point, the white dwarf stops cooling. It's reached equilibrium with its environment. It's as cold as the universe around it. It's now a black dwarf, a cold, dark sphere of carbon and oxygen, about the size of Earth but with half the mass of the sun, no longer emitting any detectable radiation, invisible except for its gravitational influence, a stellar ghost. And this is the fate of every white dwarf in the galaxy, slowly cooling over quadrillions of years, gradually fading from blue-white to yellow to orange to red to infrared to nothing, becoming black dwarfs, becoming invisible. During the Middle Degenerate Era, Milky Way is filled with these cooling white dwarfs, trillions of them, in various stages of cooling. The youngest, formed most recently from the last red dwarfs to die, are still hot and glowing. The oldest, formed billions or trillions of years earlier from medium-sized stars like the Sun, are cool and dim, and as time passes, they all continue to cool. The galaxy grows darker, not quickly, not noticeably on human timescales, but inexorably. If you could watch the galaxy in time-lapse, speeding up billions of years into a few seconds, you'd see it gradually dimming. The remaining light sources, the white dwarfs, slowly fading like candles burning down. One by one, they cross the threshold where they no longer emit visible light. One by one, they fade into the infrared. One by one, they become black dwarfs, and the darkness deepens. But there are still occasional flashes of light, rare events that briefly illuminate the darkness. Because, even though star formation has ceased, even though all the main sequence stars are dead, stellar evolution hasn't completely stopped. There are still processes that can generate energy, still events that can produce light. The most spectacular of these are white dwarf collisions. Remember, Milky Way contains trillions of white dwarfs, and these white dwarfs are in motion. They're orbiting the galactic center. Some are in binary systems, two white dwarfs orbiting each other. And over vast timescales, orbital dynamics can bring white dwarfs together. When two white dwarfs collide, or when a white dwarf pulls material from a companion star, several things can happen depending on the masses involved. If the combined mass exceeds about 1.4 solar masses, a limit called the Chandrasekhar limit, something dramatic occurs. The added mass pushes the white dwarf over a critical threshold. The pressure and temperature in the core increase, and suddenly, the carbon and oxygen that make up the white dwarf begin to fuse, not gradually, not controlled, but all at once. It's a runaway thermonuclear reaction. Within seconds, the entire white dwarf undergoes explosive carbon fusion. The energy released is enormous. The white dwarf doesn't just heat up, it explodes, completely, violently. This is a Type 1a supernova, one of the most energetic events in the universe. For a few weeks, this single exploding white dwarf can outshine an entire galaxy of normal stars. In the dark, quiet Milky Way of the degenerate era, such an explosion would be visible across the entire galaxy and far beyond. It would briefly illuminate any surviving planets, casting light on worlds that have been in darkness for trillions of years. Any hypothetical observer watching the galaxy from outside would see a sudden bright flare, a point of light that wasn't there before, suddenly shining brilliantly, then gradually fading over the course of weeks or months. And then darkness again. These Type 1. As supernovae are rare. In a typical galaxy, during the stelliferous era, they occur maybe once every few hundred years. But we're not in the stelliferous era anymore. We're in the degenerate era, where white dwarfs are drifting apart, where the galaxy is less dense, where interactions are less frequent. The rate of these supernovae drops, maybe one every few million years, then one every few billion years, then even less frequent as the white dwarfs continue to spread out, their orbits evolving due to gravitational interactions with other objects. But they still happen occasionally, and each time one does, it's a reminder that the galaxy isn't completely dead yet, that there's still energy available, that fusion can still occur under the right conditions. The supernova scatters material across space: carbon, oxygen, iron, nickel, all the elements created in the explosion. And, in principle, if there were any gas around to collect this material, if star formation were still possible, new stars could form from this enriched matter. But there's no gas. Star formation ended trillions of years ago. The material from the supernova just spreads out into the void, gradually becoming more and more diffuse, eventually cooling and becoming just another component of the sparse interstellar medium. Another type of collision can also occur. Two neutron stars can collide. Neutron stars are even denser than white dwarfs. They're the collapsed cores of massive stars, objects with about 1.4 to 2 solar masses compressed into a sphere only about 20 kilometers across. They're so dense that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. When two neutron stars collide, the result is spectacular. The collision releases an enormous amount of energy, much of it in the form of gravitational waves that ripple through space-time at the speed of light. But it also produces light. A tremendous amount of light. The collision heats the neutron star material to billions of degrees. It creates a fireball that shines across the electromagnetic spectrum, from radio waves to gamma rays. And it produces heavy elements, including gold and platinum and uranium, through rapid neutron capture. For a brief time, perhaps a few seconds to a few minutes, this collision can be one of the brightest objects in the universe. And then it fades, either forming a more massive neutron star or, if the combined mass is high enough, collapsing into a black hole. These neutron star collisions are even rarer than white dwarf supernovae, but they still happen occasionally during the degenerate era, and each time one does, it provides a brief flash of light in the darkness. A momentary reminder of the violent processes that used to be common when stars were still dying, when supernovae were frequent, when the galaxy was young and active. But as time passes, as trillions of years turn into quadrillions, even these rare events become rarer. The white dwarfs continue to spread out. The neutron stars become more isolated. The galaxy grows larger as its structure slowly evolves due to gravitational interactions. The objects that make up the galaxy, the white dwarfs and neutron stars and black holes and any surviving planets, are moving on orbits that gradually change over time. Some objects get flung outward, escaping the galaxy entirely. Others spiral inward, eventually falling toward the galactic center. This process, called dynamical relaxation, takes an incredibly long time. But we have incredibly long timescales to work with. Over about 100 trillion years, a significant fraction of the galaxy's stellar remnants are either ejected into intergalactic space or fall into the supermassive black hole at the galactic center. The galaxy is evaporating. Not literally, it's not turning into gas, but its structure is dissolving. The objects that once made up a coherent galaxy are spreading out, becoming more diffuse, losing their gravitational connection to each other. By 100 trillion years after the Big Bang, Milky Way has changed dramatically from even its early degenerate era appearance. The galaxy is much larger and much less dense. Many of its stars have been ejected. Many others have fallen into the central black hole. What remains is a much more diffuse collection of objects, no longer really a galaxy in the traditional sense, but more like a loose association of stellar remnants drifting through space. And during all of this time, during these tens and hundreds of trillions of years, something else has been happening, something subtle but ultimately crucial to the thought of everything. Matter itself might be decaying. This is where we enter uncertain territory, because we're not sure if this actually happens. But if it does, if the predictions of certain theoretical physics models are correct, then what comes next is even stranger than everything we've talked about so far. Protons, the positively charged particles in atomic nuclei, appear to be stable. We've never observed a proton decaying, and we've looked very carefully. There are detectors deep underground, shielded from cosmic rays, watching enormous tanks of purified water, waiting to see just one proton decay. They've been watching for decades. So far, nothing. Based on these experiments, we can say that if protons do decay, their half-life is at least 10 to the 34th power years. That's an incomprehensibly long time. Far longer than the current age of the universe. Far longer than the time it takes for stars to burn out. But some theories, particularly theories that attempt to unify all the fundamental forces of nature, predict that protons should decay, just extremely slowly. If these theories are correct, if protons have a half-life somewhere between 10 to the 34th and 10 to the 36th power years, then something remarkable happens during the late degenerate era. The stellar remnants themselves begin to disintegrate. A white dwarf is made of atoms, carbon and oxygen atoms mostly. Each atom has a nucleus made of protons and neutrons. If protons decay, these nuclei gradually fall apart. Very slowly, incredibly slowly. But given enough time, a significant fraction of the protons in a white dwarf will decay. When a proton decays, according to most models, it turns into a positron, a gamma-ray photon, and a pion that quickly decays into more photons. Each decay releases a small amount of energy. And here's what's interesting. A white dwarf undergoing proton decay is actually generating energy. Not much, about 400 watts for an entire white dwarf, roughly enough to power a few incandescent light bulbs. But it's not zero. The white dwarf isn't completely dark. It's glowing faintly from the energy of proton decay. This is hard to wrap your mind around. We're talking about an era so far in the future that all the stars have burned out. The white dwarfs have cooled to black dwarfs. The galaxy has mostly evaporated, and yet the stellar remnants are still producing light, not from fusion, not from thermal radiation, but from the decay of matter itself, from the gradual disintegration of protons that have been stable for tens of trillions of years, but are now finally falling apart. An entire galaxy of these slowly disintegrating black dwarfs would have a total luminosity far less than a single hydrogen-burning star from the stelliferous era. But it's not zero. The galaxy isn't completely dark. Not yet. It's producing light from a fundamentally different source than it ever has before. This continues for timescales that make the degenerate era up to this point look brief. With a proton half-life of 10 to the 34th years, it takes about 10 to the 37th years for a significant fraction of the protons in a stellar remnant to decay. During this time, the black dwarfs gradually dissolve. Their mass decreases as protons decay into lighter particles and radiation. Their structure weakens as the atomic nuclei that hold them together fall apart. Eventually, after about 10 to the 40th years, essentially all the ordinary matter in what used to be Milky Way has decayed. The black dwarfs are gone. The neutron stars, which are also made of protons and neutrons, albeit in an exotic high-density state, have also decayed. Even the planets, the asteroids, the chunks of rock and ice that have been floating through space since the stelliferous era have disintegrated. What's left? Black holes and elementary particles, electrons, positrons, neutrinos, photons, all of it spread across vast distances as the universe continues to expand. The stellar remnants that defined the degenerate era have been replaced by a thin gas of subatomic particles. The density is incredibly low, lower than the best vacuum we can create on Earth, lower than interstellar space during the stelliferous era. Unimaginably low, and this is the transition point. The moment when the degenerate era ends and the black hole era begins. The age when the only significant structures left in what used to be a galaxy are black holes. Now, I need to pause here and acknowledge something. Everything I've just described about proton decay is theoretical. We don't know for certain that protons decay. It's possible they're absolutely stable, that they last forever. If that's the case, if protons don't decay, then the stellar remnants don't disintegrate. They persist indefinitely. Black dwarfs continue to exist as cold, dark spheres of carbon and oxygen forever. Neutron stars continue as ultra-dense balls of neutrons forever. The degenerate era lasts forever, or at least it lasts until something else happens. There are other processes that could destroy stellar remnants even if protons are stable. Quantum tunneling, for instance. Over incredibly long timescales, quantum mechanics predicts that matter can spontaneously rearrange itself into lower energy configurations through a process called quantum tunneling. A stellar remnant could potentially tunnel into a black hole or into a different configuration of matter. But the timescales for this are even longer than those for proton decay. We're talking about 10 to the many hundreds of powers of years, numbers so large that they're almost meaningless. But for the purpose of this journey, let's assume proton decay happens. Let's assume that stellar remnants do eventually disintegrate, leaving only black holes. Because that leads us to the next phase. And the next phase is where things get truly bizarre. Where we encounter phenomena so strange that they challenge our basic understanding of reality. Let me tell you about the black hole era, We are now approximately 10 to the 40th years after the Big Bang. For context, the current age of the universe is about 10 to the 10th years. We've jumped forward by 30 orders of magnitude. If the current age of the universe was 1 second, we're now at about 30 trillion years later. The timescale is almost incomprehensible, but we can describe what's happening. All the ordinary matter in what used to be Milky Way has decayed. The white dwarfs are gone. The neutron stars are gone. Even the planets and asteroids have disintegrated into subatomic particles. What remains are black holes of various sizes, stellar mass black holes formed from the collapse of massive stars billions or trillions of years ago, intermediate mass black holes formed from the merger of stellar mass black holes or from the collapse of very dense star clusters, and at what used to be the galactic center, a supermassive black hole containing millions or billions of solar masses, formed from the merger of the Milky Way's and Andromeda's central black holes, plus all the material that's fallen into it over the eons. These black holes are the last macroscopic objects, the last structures that could reasonably be called things rather than just diffuse clouds of particles. And they're going to dominate the universe for a very long time, far longer than stars dominated, far longer than any previous era, because black holes are incredibly stable. They don't burn fuel. They don't cool down like white dwarfs. They just exist, warping space-time around them, creating regions where gravity is so strong that not even light can escape. But black holes aren't actually eternal. They're not truly black. In 1974, Stephen Hawking made one of the most remarkable predictions in theoretical physics. He showed that black holes emit radiation. This was completely unexpected. By definition, a black hole is a region where gravity is so strong that nothing can escape once it crosses the event horizon. How could a black hole emit anything? The answer lies in quantum mechanics. According to quantum field theory, empty space isn't actually empty. It's filled with quantum fluctuations. Virtual particle pairs constantly popping into existence, existing for a tiny fraction of a second, then annihilating each other. An electron and a positron appear. Then they collide and vanish. This happens everywhere, constantly. Normally, we don't notice these virtual particles because they exist so briefly and always annihilate. But near the event horizon of a black hole, something interesting can happen. A virtual particle pair forms just outside the horizon. Before they can annihilate, one particle falls into the black hole while the other escapes. The escaped particle is now real. It's no longer virtual. It carries energy away from the black hole. To an outside observer, it looks like the black hole emitted a particle. This is Hawking radiation. And here's the crucial point. That escaped particle carried away energy. And energy is related to mass through Einstein's equation E equals mc squared. If the black hole lost energy, it lost mass. The black hole got smaller. This process continues. Particle pairs form. One falls in, one escapes. Each time, the black hole loses a tiny bit of mass. Over enormous timescales, this adds up. The black hole slowly evaporates. Now, for large black holes, this process is incredibly slow. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. Bigger black holes are colder. A black hole with the mass of the Sun has a temperature of about 60 nanokelvins. That's 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation, which is currently about 2.7 Kelvin. A solar mass black hole won't emit Hawking radiation faster than it absorbs energy from the cosmic background. It will actually grow, not shrink, at least for now. But the universe is expanding, and as it expands, the cosmic microwave background cools. It's proportional to 1 over the scale factor of the universe. As the universe gets larger, the background radiation gets colder. Eventually, after about 10 to the 19th years, the cosmic background radiation will have cooled below 60 nanokelvins. At that point, even stellar mass black holes will be warmer than their surroundings, and they'll start to evaporate, very slowly. A solar mass black hole takes about 10 to the 67th years to completely evaporate through Hawking radiation. Let me write that out in a way that might help you grasp it. That's 10 followed by 67 zeros years. A number so large that if you wrote it out in regular notation at normal font size, it would stretch for about 30 meters. That's how long it takes for a solar mass black hole to evaporate, and supermassive black holes take even longer. The evaporation timescales with the cube of the mass. A black hole with 1 billion solar masses takes about 10 to the 100th years to evaporate. A Google years. The number that gives us the term Google. That's 10 followed by 100 zeros. A number so large that there aren't enough particles in the observable universe to represent it if you assigned 1 particle per digit. During the black hole era, these slowly evaporating black holes are essentially the only things that exist. Everything else is gone. Stars burned out trillions of years ago. Stellar remnants decayed quadrillions of years ago. What remains is a vast expanding universe filled with a dilute gas of particles, photons, electrons, positrons, neutrinos, and scattered throughout this diffuse gas, incredibly far apart, isolated by distances that dwarf the size of the observable universe today, are black holes, slowly, imperceptibly evaporating. For most of a black hole's lifetime, the Hawking radiation it emits is incredibly weak. The black hole is massive and cold. The particles it emits have very low energy. The radiation is mostly photons with wavelengths longer than the black hole itself. These photons don't carry much energy. The black hole is losing mass, but very, very slowly. If you could somehow observe a stellar mass black hole during the early part of its evaporation, you wouldn't see anything. The Hawking radiation would be too weak to detect with any reasonable instrument. The black hole would be invisible, just a region of warped space-time slowly, almost imperceptibly shrinking. But as a black hole evaporates, as it loses mass, something interesting happens. Its temperature increases. Smaller black holes are hotter. This creates a feedback loop. As the black hole shrinks, it gets hotter. As it gets hotter, it radiates more energy. As it radiates more energy, it shrinks faster. The evaporation accelerates. For most of the black hole's lifetime, this acceleration is negligible. the black hole loses mass at an almost constant rate. But in the final stages, in the last few years of a black hole's existence, the evaporation becomes rapid. When a black hole has shrunk to about the mass of a large mountain, it's radiating intensely. The Hawking radiation includes not just photons but massive particles, electrons and positrons, muons, even heavier particles. The black hole is glowing, visibly glowing, getting brighter and hotter as it shrinks. And then, in the final moments, when the black hole has shrunk to about the Planck mass, about 22 micrograms, it explodes. Not gradually, not gently, but in a final burst of energy. All the remaining mass is converted into radiation in a fraction of a second. The black hole has evaporated completely. Nothing remains except the radiation spreading out into space. This is how black holes die, and this is how the black hole era ends. One by one, over timescales that dwarf everything we've discussed so far, the black holes evaporate. The stellar mass black holes go first, after about 10 to the 67th years. The intermediate mass ones take longer. The supermassive ones, the former galactic centers like the black hole at the heart of Milky Way, take longest of all. But eventually, after about 10 to the 100th years, even these titans evaporate. The last black hole in what used to be Milky Way, the supermassive black hole that formed from the merger of the Milky Way's and Andromeda's central black holes, that accumulated mass from countless stars and gas clouds over the eons, that survived the entire stelliferous era, the entire degenerate era, and almost the entire black hole era. This last black hole finally evaporates. For a brief moment, measured in fractions of a second, it shines as brightly as a star as it undergoes its final explosion, and then it's gone, completely gone. All its mass has been converted into radiation, into photons and neutrinos spreading out into the void at the speed of light. And with that final flash, Milky Way, the galaxy that formed from the collision of the Milky Way and Andromeda, ceases to exist in any meaningful sense. There are no structures left, no objects, no concentrations of matter or energy, just a region of space that used to contain a galaxy, now filled with nothing but an incredibly diffuse gas of elementary particles. Photons from the evaporated black holes, electrons and positrons left over from decayed matter, neutrinos that have been traveling through space since the early universe, all of it spread across distances so vast that the particles almost never interact. The density is so low that you could travel for trillions of light years without encountering a single particle. This is the transition into the final era, the dark era, the end of everything. Let me tell you what happens next. We are now about 10 to the 100th years after the Big Bang, a Google years. To put this in perspective, if every particle in the observable universe represented 1 year, we would need more than 10 trillion observable universes worth of particles to represent this amount of time. The number is so large, it loses all connection to human experience. It's just a mathematical abstraction. But we can still describe the state of the universe at this time. All the black holes have evaporated. All the matter has decayed, assuming proton decay occurs. What remains is a universe that has expanded to an incomprehensibly vast size, filled with an incomprehensibly dilute gas of elementary particles. The density is about 1 particle per cubic light year, maybe even lower. For comparison, the best vacuum we can create on Earth has about 100,000 particles per cubic centimeter. Interstellar space during the stelliferous era had about 1 atom per cubic centimeter. The average density of the universe today is about 5 protons per cubic meter. But in the dark era, the density is about 1 particle per cubic light year. A light year is about 10 trillion kilometers. A cubic light year is about 10 to the 39th cubic meters. 1 particle per cubic light year means a density of about 10 to the minus 39 particles per cubic meter. That's incomprehensibly empty, unimaginably sparse. If you were somehow a conscious observer in this era, which you couldn't be because there's no energy available to run any kind of information processing system, but if you were, you could travel at the speed of light for years without encountering a single particle. The universe has become, for all practical purposes, empty. But it's not just empty, it's also cold, incredibly cold. The cosmic microwave background, which is currently about 2.7 Kelvin, has cooled to nearly absolute zero, maybe 10 to the minus 100 Kelvin, or even lower, depending on how much the universe has expanded. At this temperature, essentially nothing can happen. Chemical reactions require a certain temperature range to proceed. Nuclear reactions require even higher temperatures. But in the dark era, the temperature is so low that no reactions can occur. No processes can proceed. No change can happen. The universe has reached a state called maximum entropy. Let me explain what this means and why it's the end of everything. Entropy is a measure of disorder. More precisely, it's a measure of how spread out energy is in a system. High entropy means energy is evenly distributed. Low entropy means energy is concentrated in certain places. The second law of thermodynamics states that entropy always increases in a closed system. Energy flows from concentrated to dispersed. Heat flows from hot to cold. Order becomes disorder. This law is one of the most fundamental in all of physics, and it has profound implications for the fate of the universe. In the early universe, just after the Big Bang, entropy was low in a certain sense. The universe was hot and dense and relatively uniform, but all the energy was concentrated in a small volume. As the universe expanded and cooled, entropy increased. Stars formed, concentrating gravitational energy. But when they burned, they converted that concentrated energy into dispersed radiation. Net entropy increased. Galaxies formed, creating structure. But the processes within galaxies, star formation and death, increased entropy even more. Every process that's occurred in the universe, from the fusion of hydrogen in stars to the evaporation of black holes, has increased the total entropy. And in the dark era, the universe has reached maximum entropy, or very close to it. All the energy that existed in the early universe is now spread out as evenly as possible across the vastness of space. There are no more concentrations, no more gradients, no more hot spots or cold spots. Everything is the same temperature, just barely above absolute zero. Everything is maximally dispersed, and when a system reaches maximum entropy, nothing more can happen. Change requires energy gradients, requires some place that's hotter or denser or higher energy than some other place, requires the ability for energy to flow from one state to another. But in maximum entropy, there are no gradients. Energy is already as spread out as it can be. There's nowhere for it to flow, no change that can occur, no process that can proceed. The universe has reached equilibrium, and it will remain in equilibrium forever. This is heat death. Not death in the sense of destruction, but death in the sense of ending, the end of all activity, the end of all change, the end of all events. The universe hasn't been destroyed. Space still exists, time still passes, at least mathematically, but nothing happens. There are no events, no changes, no processes. An electron might drift through space for trillions of years without encountering anything. A photon might travel forever without interacting with a single particle. Everything that can happen has already happened. Everything that can change has already changed. The universe has reached its final state, and it's not dramatic, it's not violent, it's not even particularly interesting. It's just static, unchanging, eternal, a vast, cold, empty space filled with particles so dispersed that they might as well not exist. This is the ultimate fate of the Milky Way, of Milkomeda, of every galaxy in the universe. They all follow this same path. Formation, evolution, star formation and death, collision and merger, the slow exhaustion of resources, the dimming of the last stars, the evaporation of the remnants, and finally, dissolution into the maximum entropy state, the heat death, the final silence. And here's something that's both disturbing and oddly beautiful. At this point, space and time lose much of their meaning. Without events to mark the passage of time, without change to distinguish one moment from another, time becomes an abstract mathematical concept rather than something experienced or measurable. Yes, you could still count seconds if you had a clock. The equations of physics still include time as a variable, but experientially, phenomenologically, time has stopped. One moment in the dark era is indistinguishable from any other moment. Nothing is different between now and 10 trillion years from now. There are no events to mark time's passage, no changes to observe, no before and after. The universe exists in a kind of eternal now, a timeless state where past and future become meaningless because nothing ever changes. Space is similarly strange, without structures to define locations, without reference points to measure distances from, the concept of a position becomes abstract. Yes, particles exist at locations in space, but when they're separated by such vast distances that they never interact, when you could travel in any direction forever without encountering anything, the distinction between here and there becomes meaningless. The universe is simultaneously everywhere and nowhere, full and empty, existing and not existing. It's almost like a philosophical state rather than a physical one. Now, you might be wondering, is there any hope, any possibility that something could happen to break this eternal stasis? Could the universe somehow restart? Could new structures emerge from the maximum entropy state? The honest answer is we don't know. Our physics doesn't really apply anymore at these conditions. We're so far beyond anything we can test or observe that we're essentially speculating. But there are some interesting possibilities. Some physicists have suggested that quantum mechanics might allow for spontaneous fluctuations even in the maximum entropy state. These would be incredibly rare, incredibly unlikely, but over infinite time, unlikely things eventually happen. There's a tiny, infinitesimally small but non-zero probability that a random quantum fluctuation could spontaneously create a structure out of the vacuum, not just particle pairs, but larger objects, perhaps even a conscious brain, complete with memories and experiences that exists for a brief moment before dissipating. These are called Boltzmann brains, named after the physicist Ludwig Boltzmann, who explored these ideas in the context of thermodynamics. The idea is that if you wait long enough, truly long enough, longer than any timescale we've discussed, random quantum fluctuations might occasionally create organized structures. You might get a random atom, even more rarely, a random molecule. Extraordinarily rarely, a random brain. And incomprehensibly rarely, you might even get a random star or planet or galaxy, all spontaneously emerging from quantum vacuum fluctuations. The timescales for this make the heat-death timescale look brief. We're talking about 10 to the 10 to the 100 years. That's not 10 to the 100. That's 10 to the power of 10 to the 100. A number so large that to write it out, you'd need 10 to the 100 digits. The universe doesn't contain enough particles to write this number if you used one particle per digit. But mathematically, given truly infinite time, these events would eventually occur. You might occasionally get a brief moment of structure in the otherwise maximum entropy vacuum, a flash of complexity in the eternal darkness, a single conscious thought in an otherwise thoughtless cosmos, and then it would dissipate, and the darkness would return for timescales even longer than the time it took for that structure to appear. Another possibility, suggested by some cosmologists, is that the universe might not remain in this state forever. Perhaps the properties of dark energy, the mysterious force driving the universe's accelerating expansion, change over time. Perhaps the expansion eventually reverses, leading to a big crunch where the universe collapses back in on itself, mirroring the Big Bang but in reverse. Or perhaps the vacuum itself is unstable. Perhaps space-time as we know it is not in its lowest energy state. Perhaps there's a lower energy configuration possible, and the universe might quantum tunnel into this new state, essentially rebooting with different physical laws and starting a new cycle of evolution. Or perhaps, and this is the most speculative possibility, our universe is part of a larger multiverse. Perhaps what we call the universe is just one bubble in a vast cosmic foam. Perhaps other bubbles exist with different properties, different histories. Perhaps new bubbles are constantly forming through quantum fluctuations or other mechanisms we don't understand. If this is true, then the heat death of our universe is just one local event in a much larger structure that continues beyond our ability to observe or comprehend. But these are all speculations. Based on what we currently understand about physics, based on the laws that govern our universe as we observe them, the most likely scenario is that the universe expands forever, cools forever, and remains in the dark era forever. The heat death is permanent. The maximum entropy state is final. The universe will remain cold and dark and empty, with particles so dispersed they never interact, for all eternity. And this means that the light from the Milky Way, the light from every galaxy, the light from every star that has ever shone, has not just gone out. It's been dispersed so thoroughly, spread so thin, diluted so completely by the expansion of space, that it effectively no longer exists in any meaningful sense. The photons still exist. They're still traveling through space, but they're stretched to wavelengths longer than the observable universe. They have energies so low that they're indistinguishable from the vacuum fluctuations of space-time itself. They can never again interact with anything. They can never again be detected or measured or used to see by. The light is gone, not just dimmed, not just faded, but gone, dissipated into the maximum entropy state, rendered meaningless by the heat death. The Milky Way has run out of light, not just in the sense that its stars have burned out, but in the deeper sense that the light itself, all the photons produced by all the stars over the entire stelliferous era, has been stretched and dispersed until it's no longer light in any meaningful way. The galaxy is not just dark, it's gone, completely gone, dissolved, dispersed, reduced to a sparse scattering of elementary particles spread across distances so vast that no two particles will ever interact again. This is the end, the final end, the point beyond which nothing more can be said because nothing more happens. The universe continues to exist, mathematically. Space still extends infinitely. Time still progresses. But there are no events, no changes, no stories to tell, just eternal, unchanging, maximum entropy equilibrium. Forever. And yet, despite all of this, despite the ultimate fate of everything, despite the heat, death, and the maximum entropy and the eternal darkness, something profound remains. Memory, not literal memory, not information stored anywhere, but the fact that it happened, the fact that for a brief time, measured in trillions of years, but brief compared to the eternal dark era that follows, the universe was alive. Stars burned, galaxies shone, complexity emerged, life appeared, consciousness arose. Beings existed who could look up at the stars and understand what they were seeing. The universe examined itself through eyes that evolved from stardust. It understood itself through minds made of atoms forged in stellar cores. You are part of that story. You are one expression of the universe's brief flowering of complexity and awareness. You exist during the Golden Age, during the stelliferous era, during the time when light is abundant and life is possible, and that fact, the fact that you are here now, during this precious moment in cosmic history, that cannot be erased. Even after the heat death, even after maximum entropy, even after the universe has been dark and cold for googolplex years, the fact remains that you existed, that you were conscious, that you experienced this moment, that you understood, at least partially, the vast cosmic story of which you are a part. That fact is eternal in a way that physical structures are not. It's a fact about the history of the universe, and while the universe may forget, while there may be no records left, no information stored anywhere after the heat death, the fact itself remains true. It happened. You happened. The Milky Way shone, stars burned, light illuminated the darkness. Consciousness emerged and contemplated the cosmos. This happened. This was real. This mattered. And no amount of time, no heat death, no maximum entropy can change that fundamental fact. So let me bring this back to right now, to this moment, to your life. Because that's really what this entire journey has been about. Not just learning about cosmic timescales and the death of galaxies, but understanding what it means to exist during the age of light, what it means to be alive right now. You've traveled with me through time itself, through billions and trillions and quadrillions of years, through the collision of galaxies and the death of stars and the evaporation of black holes and the heat death of the universe. You've seen the end of everything, the final darkness, the maximum entropy state where nothing can ever happen again. And having seen that, having understood the ultimate fate of the Milky Way and every galaxy in the universe, what should you do with that knowledge? How should it change how you live your life right now? First, appreciate the present moment. Really appreciate it. You're alive during the stelliferous era, the age of stars. The universe is full of light, full of energy, full of possibility. This won't last forever, but it's happening now, and you're here to experience it. Look up at the stars tonight. Really look at them. Understand that each one is a sun. Each one is a fusion reactor converting mass into energy. Each one is temporary. They're burning through a finite fuel supply. One day they'll all be gone. But they're here now. They're shining now. And you can see them. Second, recognize the preciousness of consciousness. You are aware. You can think, you can feel, you can understand. This is extraordinary. The universe spent billions of years evolving from a hot, dense state to stars, to planets, to life, to consciousness. And now you're here. You're one of the ways the universe knows itself. That's not nothing. That's remarkable. Don't waste your consciousness on things that don't matter. Don't spend your finite time and attention on trivia and distraction. Be present. Be aware. Experience your life fully, because consciousness might be rare. It might be temporary. This might be a brief window in cosmic history when matter can organize itself into patterns complex enough to think and feel. Don't squander your moment of awareness. Third, gain perspective on your problems and anxieties. I'm not saying your problems don't matter. They do. They're real. They affect you. But when you understand the cosmic context, when you see your life against the backdrop of billions of years of cosmic evolution, it helps you distinguish what's truly important from what's just noise. The argument you had with a friend, the deadline at work, the political outrage on social media. These things feel huge in the moment, but measured against cosmic time, against the billions of years before you existed and the trillions of years after you're gone, they're tiny, ephemeral, fleeting. This doesn't mean they don't matter. It means they matter proportionally. They matter in the context of your brief life, but they don't define the universe. They don't determine the fate of everything. So deal with them, address them, but don't let them consume you. Don't let temporary frustrations obscure the bigger picture. Fourth, connect with others. You're not alone in this. There are billions of other humans alive right now, all of them also made of stardust, all of them also conscious products of cosmic evolution, all of them also experiencing this brief moment during the age of light. Your relationships, your connections, your love for others, and their love for you. These are some of the most precious things in existence, because they're temporary, because they're rare, because they only exist during this brief window when consciousness is possible. Love deeply, connect meaningfully, be present with the people who matter to you, because one day you'll be gone, they'll be gone, everyone will be gone, the stars will burn out, the galaxies will dim, and none of this will remain, except the fact that it happened, the fact that you loved and were loved, the fact that you connected, the fact that you weren't alone in the darkness. Fifth, create something, leave a mark, not because you'll be remembered forever, because you won't. After the heat death, there will be no one to remember anything, but because creation is an expression of consciousness. Because making something, whether it's art or science or a business or a family or just a moment of beauty, is a way of participating in the universe's brief flowering of complexity. Your stardust that can think and create. That's miraculous. Use that gift. Make something. Add something to the brief age of light before the darkness returns. And finally, accept the ending. Accept that everything is temporary. Accept that you will die. Your loved ones will die. Humanity will die. The earth will die. The sun will die. The Milky Way will die. Everything dies. Everything ends. Everything fades. And that's okay. That's how it's supposed to be. Permanent things, eternal things, unchanging things are boring. They don't evolve, they don't grow, they don't mean anything because they have no context, no contrast. It's the temporary nature of things that makes them beautiful. The fact that stars burn out makes their light more precious. The fact that life is finite makes it more valuable. The fact that consciousness is rare makes it more remarkable. The fact that you won't live forever makes every moment you have infinitely important. So don't rage against the dying of the light. Don't deny the ending. Don't pretend things last forever when they don't. Accept it. Embrace it. Let the temporary nature of existence make you more present, more aware, more appreciative of what you have right now. Because right now is all you have. Right now is all anyone has ever had. The past is gone. The future isn't here yet. Only the present is real. Only this moment exists. And in this moment right now, the stars are shining. The universe is full of light. You are alive and conscious and capable of understanding your place in the cosmic story. That's enough. That's more than enough. That's everything. We've reached the end of our journey. We've traveled from the present moment through the collision of galaxies, through the death of stars, through the evaporation of black holes, all the way to the heat death and the maximum entropy state. We've seen what happens when the Milky Way finally runs out of light. And having seen it, having understood it, we return to right now, to this moment, to the present, where the stars still shine, where you still exist, where consciousness still illuminates the darkness. Thank you for taking this journey with me. Thank you for investing your time, your finite and precious time, in understanding the cosmic context of your existence. If this resonated with you, if it changed how you see things, please consider subscribing to this channel. Hit that like button. Share this with someone who might benefit from this perspective. Help build a community of people who understand their cosmic context, who appreciate the preciousness of the present moment, who recognize that we're living during the age of light. And now, go outside tonight if you can. Look up at the stars. Really see them. Understand what they are. Understand how long they took to form. Understand that they're temporary. Understand that one day, trillions of years from now, they'll all be gone. And then appreciate them. Appreciate that they're here now. Appreciate that you're here now. Appreciate this cosmic moment when the universe shines brightest and you're alive to see it. The Milky Way will run out of light, but not today. Not in your lifetime. Not for trillions of years. Today, the stars burn. Today, you exist. Today is the time of light, and you're here for it. That's the gift. That's the miracle. That's the only thing that truly matters. Be here, be present, be aware, and let the knowledge of cosmic endings make this cosmic beginning, this brief age of light and life and consciousness, infinitely more precious than it already is. Thank you. Good night, and may you never look at the stars the same way again. Let me spend a few more moments with you here before we truly close this journey, because I want to make sure you carry something meaningful away from this exploration, something that changes not just what you know, but how you see the world, how you experience your life. We've covered so much ground together. We've journeyed through timescales that break human intuition. We've watched events that won't happen for trillions of years. We've witnessed the slow, inevitable dimming and death of everything. And I know that can feel heavy. It can feel overwhelming. It can even feel depressing if you let it. But I don't want you to feel depressed. I don't want you to walk away from this feeling soul or meaningless or nihilistic, because that would be missing the point entirely. The point isn't that nothing matters, because everything ends. The point is that everything matters precisely because it ends. Let me explain what I mean by walking through some concrete examples. Think about a sunset. Why is a sunset beautiful? Not just visually, though it is, but emotionally. Why does watching the sun sink below the horizon move us? Why do we stop what we're doing to watch? Why do we take photos? Why do we share them with others? It's because the sunset is temporary. It lasts maybe 10 or 20 minutes. Then it's over. The colors fade, the light dims, night falls, and you can never get that exact sunset back. Tomorrow's sunset will be different. The clouds will be arranged differently. The colors will be different hues. The feeling will be unique to that moment. If sunsets lasted forever, if the sun hung at the horizon eternally, painting the sky in oranges and reds and purples indefinitely, would they be beautiful? No, they'd be ordinary, boring even. Background noise. It's the temporary nature of the sunset, the fact that it's fleeting, that makes it precious, that makes us pay attention, that makes us appreciate it. The same is true for everything. A meal is more delicious because you'll finish it. A song is more moving because it has an ending. A vacation is more memorable because you had to come home. A relationship is more precious because both people are mortal. The temporary nature of things is what gives them meaning, what makes them worth experiencing, what makes them beautiful. And this applies at every scale. Your life is meaningful because it's finite. If you lived forever, if you had infinite time to do everything, nothing would be urgent, nothing would be important. You could always do it later, forever later. But because your time is limited, because you only get maybe 80 years if you're lucky, every moment matters. Every choice counts. Every experience is unique and unrepeatable. The same is true for humanity as a species. We won't last forever. Maybe we'll survive for another few thousand years, maybe a few million if we're incredibly lucky and incredibly capable. But eventually, something will get us. Maybe we'll destroy ourselves. Maybe a cosmic catastrophe will wipe us out. Maybe we'll evolve into something so different we wouldn't recognize it as human anymore. But Homo sapiens, as we know it, will not last forever. And that makes what we do now matter. The art we create, the knowledge we discover, the love we share, the civilizations we build, all of it is temporary. All of it will eventually be lost. But that doesn't make it meaningless. It makes it precious. It makes it worth doing. It makes it important that we do it well, that we do it with intention and care, because we won't get another chance. And the same is true at the cosmic scale. The stelliferous era, the age of stars, will not last forever. We've spent this entire journey exploring exactly how it will end. But it's happening now. Right now, stars are burning, galaxies are glowing, the universe is full of light and energy and possibility. This won't last forever. But it's real now. It's happening now. And that makes it beautiful. That makes it worth appreciating. That makes it worthy of our attention and wonder and awe. So, when I tell you that the Milky Way will run out of light, when I describe the heat death and the maximum entropy state and the eternal darkness, I'm not trying to depress you. I'm trying to help you see how precious the light is while we have it. I'm trying to help you appreciate that you're alive during the time when stars shine, that you're here during the cosmic golden age, that you have this brief opportunity to exist and experience and understand. And I'm trying to help you see that your life, brief as it is, matters, not because it lasts forever, but because it happens at all. You are a pattern of organized matter and energy. You're a temporary fluctuation away from equilibrium. You're a brief moment of consciousness in an otherwise unconscious universe. You're stardust that can think and feel and wonder. And one day, you won't be. The pattern will dissolve. The organization will break down. The consciousness will cease. You'll return to the state you were in before you were born. Non-existence. Unconsciousness. The universe will go on without you, just as it went on for billions of years before you existed. But the fact that you exist now, in this moment, that's not nothing. That's not meaningless. That's extraordinary. That's a miracle in the truest sense of the word. Not a supernatural miracle, but a natural one. The miracle of complexity emerging from simplicity. The miracle of consciousness arising from matter. The miracle of the universe becoming aware of itself through beings like you. So, here's what I want you to take away from this journey. Here's the lesson I hope you'll carry with you. Don't waste your time. Don't spend your brief existence on things that don't matter to you. Don't live on autopilot. Don't sleepwalk through your one precious life because you're too distracted or too busy or too afraid to be fully present. You have maybe 80 years if you're lucky. That's about 4,000 weeks. And a significant number of those weeks have already passed. You've already used them. They're gone. You'll never get them back. The weeks you have left, those are it. That's your time. That's your opportunity. That's your chance to experience existence, to create something, to connect with others, to understand your place in the cosmos. Don't waste them. Don't throw them away on things you don't care about, on work that doesn't fulfill you, on relationships that drain you, on entertainment that numbs you without enriching you, on habits that diminish you, on fears that paralyze you. You don't have time for that. None of us do. Life is too short. The universe gives you maybe 80 years of consciousness, maybe less, probably less if we're being honest, because the last years are often diminished by illness or disability or decline. You might have 50 good years, 40, 30 if you're unlucky. That's it. That's all you get. What are you going to do with them? Here's what I hope you'll do. I hope you'll be present, really present. Not just physically in a location, but mentally and emotionally there. When you're with someone you love, be with them. Put down your phone. Turn off the TV. Stop thinking about work or your to-do list or what you're going to do later. Just be there. Look them in the eyes. Listen to what they're saying. Feel the warmth of their presence. Appreciate that they exist. Appreciate that you exist at the same time. Appreciate that you get to share this brief cosmic moment together, because one day, one of you will die, one of you will be gone, and the other will wish desperately for one more conversation, one more hug, one more moment of connection. Don't wait until it's too late to appreciate what you have. Appreciate it now, while it's here, while it's real. When you're in nature, be there. Look at the trees. Really look at them. See the complexity of their branches, the way light filters through leaves. Understand that each tree is a living thing, processing energy from the sun through photosynthesis, the same fusion process that powers stars applied through the chemical machinery of life. Feel the ground under your feet. Smell the air. Listen to the sounds. Be present in the natural world that gave birth to you. That created the conditions for your existence. That will continue long after you're gone. When you're doing something you love, something that engages you fully, do it with everything you have. Don't hold back. Don't half-ass it. Don't do it while simultaneously thinking about something else. Give it your full attention, your full effort, your full presence, because those moments when you're fully engaged, when you're in flow, when you're completely absorbed in something meaningful to you, those are the moments when you're most alive. Those are the moments you'll remember. Those are the moments that make life worth living. And when you're doing something you don't love, something you have to do but don't particularly enjoy, try to find meaning in it anyway. Find the value, find the purpose, find the lesson. Or if you can't find any of those things, change your circumstances. Life is too short to spend it doing meaningless work that diminishes you. I know that's easier said than done. I know there are constraints, financial obligations, responsibilities to others, practical realities. But within those constraints, you have more freedom than you probably realize, more agency, more choice. You can't control everything, but you can control some things. And the things you can control You should, because your time is limited. Your consciousness is finite. Your opportunity to experience existence is brief. Don't spend it in a life that doesn't feel like yours. Build a life that matters to you, that reflects your values, that allows you to be present and engaged and fully yourself. Even if it's hard, even if it requires sacrifice, even if other people don't understand. It's your life, your one life. Make it count, make it meaningful, make it yours. And please, please look up at the stars. As often as you can, on clear nights, go outside. Get away from city lights if possible. Let your eyes adjust to the darkness. And look up. See the Milky Way stretching across the sky if you're in a dark enough location. See the thousands of individual stars scattered across the dome of the heavens. See the planets, bright and steady, moving slowly against the background of fixed stars. See the moon, reflecting sunlight, going through its phases. The same moon that's been circling Earth for billions of years. The same moon that witnessed the birth of life on this planet. The same moon that will likely outlive humanity. Look at all of this and remember what you've learned. Remember that each star is a sun, that each one is fusing hydrogen into helium, converting mass into energy, pumping light out into the cosmos. Remember that they're temporary, that they're burning through a finite fuel supply, that one day they'll all be gone. Remember that the light hitting your eyes right now has traveled for years or centuries or millennia to reach you, that you're seeing the past, that you're looking back in time. Remember that you're made of the same stuff as those stars, that every atom in your body heavier than hydrogen was created in a stellar core or a supernova explosion, that you are literally stardust, literally the universe examining itself. Remember the timescales we've discussed, the billions of years of cosmic evolution that led to you, the trillions of years that will follow after you're gone, the incomprehensible spans of time during which the universe will slowly dim and cool and reach maximum entropy. Remember all of this. Let it fill you with perspective. Let it make your problems feel smaller. Let it make your blessings feel larger. Let it help you see what matters and what doesn't. And then let it go. Don't dwell on it constantly. Don't let it paralyze you with existential dread. Don't use it as an excuse for nihilism or apathy. Instead, let it motivate you. Let it inspire you. Let it help you be more present, more engaged, more alive. The stars are burning. The universe is full of light. You are here to see it. You are conscious. You are aware. You are part of the cosmic story. And that's enough. That's more than enough. That's everything. I want to thank you one more time for taking this journey with me, for spending your time, your precious and finite time, exploring the far future of the galaxy and the ultimate fate of everything. I know it's been long. I know we've covered difficult material. I know some of it is hard to wrap your mind around, but I hope it's been worth it. I hope you've gained something valuable. I hope you see the universe a little differently now. I hope you see your life a little differently. I hope you understand that you're living during a special time, a unique moment in cosmic history, a brief window when consciousness and complexity are possible, when stars shine and galaxies glow and life can emerge and evolve. This moment won't last forever, but it's happening now, and you're part of it. You're here for it. You're experiencing it. So experience it fully. Be present. Be aware. Be grateful. And remember that while the Milky Way will eventually run out of light, while everything ends, while darkness awaits in the incomprehensibly distant future, right now, in this moment, the stars are shining. Right now, you're alive. Right now is the time of light. And that's all that matters. That's all that's ever mattered. The present moment, the only moment that's ever real. This moment right here, right now, where you exist and the universe exists and consciousness bridges the gap between them. Be here for it. Be present for it. Appreciate it. Cherish it. Live it fully. Because it won't last forever. Nothing lasts forever. But it's real now. And now is all we have. Now is all we've ever had. Now is all we ever will have. So make it count. Make this moment matter. Make your brief time in the cosmic spotlight worth the billions of years of evolution that made you possible. Be here. Be present. Be alive. And when you look up at the night sky, when you see those distant suns burning in the darkness, remember this journey. Remember where those stars came from and where they're going. Remember that they're temporary, that you're temporary, that everything is temporary. And let that knowledge make them more beautiful to you. Let it make your life more precious. Let it make every moment more meaningful. The Milky Way will run out of light, but not today. Today, the galaxy shines. Today, the stars burn. Today, you exist. And today is enough.